All right, today's lesson will be dealing with the law of sines. And we've dealt with some trigonometry, sine, cosine, tangent, all the inverses, cotangent, cosecant, secant, and now we're going to use them even a little farther. But most of our work has been in right triangles, and this is going to be a little outside the box. So, if we look at what we have here, we want to solve mathematical and real-world problems by using the law of sines. Okay, we can do that. So first we better find out what the law of sines really says. So looking at this, to help us, we will look at another area of a triangle formula. So we know currently that 1/2 base times height is one of our formulas, which requires you to have the base and to be able to determine the height of your triangle. But in this case, we'd have the base. The height we would not have, but by dropping that perpendicular down, you can see, we would talk about the base being segment AC, and the height being the new segment BD, that perpendicular, well, it's not even perpendicular bisector, but it is perpendicular. So from there, we know the base is 2.5, but because of our combinations in that right triangle, the sine of 32 degrees is really BD over 2. So BD is actually equal to 2 times the sine of 32. So by using our trig functions, we're able to do a substitution. So instead of BD, we now have 2 times the sine of 32 degrees. Now we do have numbers on that right-hand side totally, and so we would write it out, multiply it out, calculate it, whatever you want to say. Our area would be approximately 1.3 units. Now, since we didn't have units, we don't know if we're in inches, feet, miles, etc. So with our calculator, knowing that that sine of 32 is not a nice number, we're going to end up with approximately a 1.3-ish answer. So using that idea that 1/2 AC sine of B, 1/2 BC sine of A, 1/2 BC sine of C, which is the relationship we used on that last one, we should be able to then rewrite it by multiplying everybody by 2, doubling everybody. And then we would write and multiply by ABC. If we do that, and ABC is just a number, and if I multiply the top and the bottom by that number, ABC over ABC is that fancy form of 1, you would get what remains here. And so we would have the sine of B over the side or edge B, the sine of angle A over side or edge A, and the sine of angle C over side or edge C. So that will be what we call the law of sines. So it's a proportion setup. It should be much nicer to use than maybe finding area of triangles, but you do have 2 choices now. The area of a triangle could be that last formula, or now maybe in some of ours, and it happens to be, if you look, that triangle we used, and let's go back, was not a right triangle. So the whole triangle by itself was not a right triangle. Just this portion we used here was a right triangle, and that's why we could use our trig function that's here. But now if we have the area of a triangle, and it's not necessarily a right triangle, we are going to be able to use that new substitution combination, which was 1/2 times the base times the height, and the height got substituted. So if we use that idea, that's where we came up with the 1/2 AC times the sine of B. And so it's the 2 edges times the angle between those 2. 2 edges multiplied together times the angle, sine of the angle inside those 2. So knowing we did that, now let's use this law of sines in a problem. And looking at it, this is more what it looks like, and it does not have to be a right triangle. We do need to use this situation when we have angle, angle, side, angle, side, angle, or side, side, angle. So think about the relationship there, and you're only going to use 2 of these at once. So maybe we'll use these 2. You don't use a proportion with 3 in. Maybe we would use these 2. Or maybe we'd use the 2 on the end, the sine of C and the sine of A. So think about your combinations that's where we're headed. All right. So with that, let's look at a situation that would work. Now, in this situation, we're looking at the angle AB, or triangle ABC. And if I notice and start looking at it, I believe we're looking at, we know that we have an angle that's 20, angle B, an angle that's 55, angle A, and then we have edge AC, which is 6. So I believe that would be an angle-angle side combination. So if we start setting it up in proportion form, remembering like angles, like edges, have to go across each other or in proportion to each other, we'll start with the sine of 20, that's angle B, is to its edge, the one that's given, 6. And then we're looking for CB, and it is paired up with the angle that's 55. So the sine of 55 is to edge A. And so what's left for you to do is work the math. And let me see, I don't remember if I've got that underneath here or not. Doesn't look like it. So we should be good to go. Yeah. So finish here, and that is cross products needs to happen next. And so A times the sine of 20 has to equal 6 times the sine of 55. And when we do that, A is what we're solving for, little a, and so we'll divide by the sine of 20. And if we divide by the sine of 20 on both sides, on the left-hand side it'll cancel out. We will have our A value. Now pick up your calculators again. Make sure that your calculator is in degree mode, because if it's not, you'll have some issues. And now go ahead and type this in, which is 6 times the sine of 55, and that has to be divided by the sine of 20. So we have a 14.37-ish value for our edge. And in relation to that 6, it's looking pretty good. I said 14.37-ish. Yep. Because you already knew that the 20 and the 55, if we went back to it, that would have given us 75. And 75 leaves us with 105 degrees, which means this edge, which is little c, has to be the longest one. We already have that one that's 6, so 14.3 looks pretty good. And again, we don't know what it is, but we'll assume it's units. So that's how we use the law of sines. Okay, now on this one, again, same situation. We want to find QR, and this would be more real life, like let's say this is a pond and we want to build a bridge or a walking path across it. But if we're looking for QR, and QR is our unknown distance that we need, and I don't know if, let's go with yellow, it might work a little better. So find QR, let's mark it. Since it's across from angle S, we'll call it little s. And so make sure, got it marked, I got green, I said I was going to use yellow, and look at that. So little s is our unknown side. Now look at what we have here again. We've got 115 and 142 for a total of 157. So we have 157 degrees, do the math. If we subtract, we've got left a 23-degree angle. So with that 23-degree angle, we now know all our angles. But since it's QR that we're looking for, we have enough information without that 23. So using angle, angle, side again, we have a setup. So here we go. We want the sine of 115. Don't change it like I just did. 115 is to its edge, 4.3, and yes, it's kilometers, but we don't need those in the mix here now. And the sine of 42 is to its edge, which was QR, the unknown, which we called S. So again, cross products again. S times the sine of 115 has to equal 4.3 times the sine of 42, divide, and we get the sine of 115 as our dividing value. So S is going to equal that calculation. Go ahead and try it. And again, if it's in perspective, we were in kilometers. So you do yours, I'll get mine, and see if we agree when we're done. I'm getting approximately a 3.17-ish. Is that what you got? If it was, x equals 3.17-ish. And this is kilometers. It sort of fits what we were doing there. The largest one had to be the 115, which is 4.3, so this is a little smaller than that. I think we're in good shape. Okay. Now, if we asked you to draw a triangle, and this is interesting, that has an A value of 7, a C value of 8, and then angle A, which remember cuts out edge A, is 41. So go ahead and draw a quick little scan. If you have a protractor and stuff, that's fine. If not, at least try to approximate your angle accurately. But label everything because that's key. Okay, if that's done, most of you would say that your angle, probably your triangle. Whoop. Not sure what happened here. Whoops, that's our old one. So I don't know. I want to go forward. So most of you would probably say your triangle looked like this. Angle A, 41 degrees, approximately right here. Side 7, and you've got your 8. A lot of you would have had a triangle that looks a lot like this. Now, if I asked you, draw a different triangle, same set, same situation. So draw a second triangle, not congruent to the first one. And this is something you got to think about. Yes, still, A has to be 7, C has to be 8, and angle A has to be 41. And we're not just talking about drawing it so that it's upside down or A, C, and B are, different perspective. We want a different looking triangle. So it's not going to look like this acute triangle that we have currently. Okay, thought about it enough? Question is there one that you can draw with these same dimensions? And if you look down here at the bottom, I have drawn it. Let's move it up. We've got that edge CB is 7 still. That edge AB is 8 still. But now angle A is much smaller than it was before. Well, sorry, it's not. Angle A is the 41 degrees, so those had to stay the same. But angle C was much smaller before. It was acute, and now we can see that angle C is definitely obtuse. Angle B also shrunk in size. So angle B became smaller and angle C became more obtuse. That took care of still the 180 combination. So interesting. We gave you the same dimensions and we got 2 triangles out of all. Is that possible on all? No. But it is possible. So that's what you have to worry about. And where'd that come from? Take a look at the blue only, which is 0 to 180, which is what's possible in a triangle. And if you start looking at cosine, nowhere along our cosine curve do you have anything that repeats. So cosine from 0 to 180 each has its own unique value. But every degree from 0 to 180, if we look at the sine wave, we cannot say that about. We're starting to get like combinations. Oh, something there and there, something here, something here. There's 2 things. There's a y value that doubles up. So there's 2 angles somewhere between. Oh, so think about what that means in perspective. We just did a triangle like that. We have the sine of theta is really equal to the sine of 180 degrees minus theta. So if I said the sine of 30, you would also know, which is over in here, Okay, sine of 30. Here's 0, so sine of 30 is about right in here, because sine of 30 is, 1/2. And if sine of 30 is 1/2, then you got to look over here and say, oh, wait a minute. Down here at the opposite end, there's also a 30. So again, sine of 30, 1/2, was about right there. You came down here, there's also another one. So that's going to be its complement. Sine of 30 equals 180 minus 30, so sine of 50. So the supplement theorem gives you two values for every sine. Cosine, they're individual. Oh, so that should open some new things. So if I said the sine of theta equals 0.127, not one we have memorized, not an exact value, but one of them we were working with, you would do definitely your inverse, because we're looking for theta. You've done that. Pick up your calculator. Did you get 7 or 173? There's two values. So the question will be, even on the next one, how do I know what triangle I have? How do I know how many triangles I have? And that's a question that we're looking at and expecting you to do. So let's pick one of these. Determine whether the given side-side angle information defines 0, 1, 2 triangles. And it could be any one of those three. Until you do the math, you don't know. So they gave us a 79-degree angle, so I'm going to do a 79, just a little quick pencil drawing is all. You got to do it. You can do it off to the side or in your work. So I'm going to do it over here. Whoops, thought I was. Okay, I'm going to do my 79-degree angle, which is not 90, but it's up there. So there's 79. And right there, and that's angle B. So actually I should have put angle B there, 79 here. And so I'm going to get A and a C. Now, across from little b is a 7.4. So right now, just for our purposes, we're going to label that 7.4. And little a, and remember these things have to go in order, so I'm going to call that angle A. That means this edge is 6.5. So we have everything. Side-side angle. And so now we have to use law signs to see if we have 1, 2, or 3. So here we go. Opposite. And I've got the sine of angle B, which is 79 degrees, is to 7.4 as the sine of angle A, which we don't know, is to 6.5. Okay? So cross products again, we're going to end up with the sine of 79 times 6.5 divided by that 7.4 has to equal the sine of A. Okay? And we know in order to find angle A, we would have to do the inverse. So let's do inverse sine. So inverse, whoops, cancel. Inverse, it's not liking it. Inverse, inverse here. And we should get our angle value. Okay, inverse sine of this combination that I'm not going to rewrite. So let's see, let's go right to our calculator and see if we can get that written in. As long as double check your numbers. 65 is the sine of A, 6.5, 7.4, 79, cross products, divide. Okay, we should be good. So let's do just a calculation first. So I'm going to do the sine of 79 times 6.5. And go ahead and divide that by the 7.4. So we have that value, and then we have to do inverse sine of that answer. And we're getting about a 59.6, we'll say. So angle A comes out to be about a 59.6 degree angle. Now, with that value, and if we go to the nearest whole number, and we probably better not because that's 60 and that's one of our equal ones, here's the thought that you have to do now to finish this question. I'm going down into part B, but that's okay. Part B will be one you do or we can do in class. So if I now currently have already a 79-degree angle that was given. So I'd have, if I'm trying to find two scenarios, if I have a 79-degree angle and I have a 59.6-degree angle, and remember now the complement, so do the complement, 180, or it's complement I called it, supplement, 180 minus that 59.6, we should have 120.4. So that could be our other combination, 120.4. Now if you do the math here, add these up, we get a 0.6, a 9 and 9 is 18, carry the 1, we get 138.6 degrees so far. So we still have room here to add to get to 180. Over here, however, if we add, we got a 0.4, a 9 and 0 is 9, a 7 and 2 is 9, and 1. Oops, we are already over. So with just those two angles, we know that there's not going to be two triangles that fit this scenario. There's only going to be one. And so we could add that, do the last math there, and all they asked was determine whether we have 1, 2, so we don't have to find any more edges. And we did that. So bring any questions you have about finding if there's 1, 2, or 0 triangles available to class with you, and we should be able to answer those questions for you.